Kelly Johnson stood in a wooden shack next to a circus tent in Burbank, California, watching his team assemble America's future in the stench of a plastics factory. The year was 1943, and Lockheed's official engineering building sat 3 miles away with proper ventilation, clean floors, and none of the urgency Johnson needed. The Army Air Forces had given him 180 days to build the XP-80 Shooting Star, America's first operational jet fighter. Johnson promised 150. He delivered in 143. The tent wasn't a romantic statement. Lockheed's main facilities were crammed with P-38 Lightning production, pushing out fighters for Europe and the Pacific at full capacity. Johnson needed space, speed, and secrecy. The circus tent provided 2 out of 3. The plastics factory next door pumped fumes that made his engineers nauseous, but the rent was cheap and the location was isolated. Johnson christened the operation Skunk Works after the moonshine factory in Al Cap's Lil Abner comic strip. The name stuck for the next 8 decades. 23 engineers worked under Johnson's command. He'd handpicked each one for their ability to solve problems without committees, memos, or approval chains. Johnson's management philosophy crystallized in that tent. Small teams, minimal bureaucracy, direct communication. If an engineer needed a decision, they walked to Johnson's desk. If a machinist spotted a design flaw, they told Johnson immediately. No middle managers, no delays. The XP-80 prototype cost $600,000, a fraction of typical military programs, because Johnson eliminated every layer between problem and solution. The jet engine itself came from Britain. Frank Whittle's centrifugal turbojet design had reached America through wartime intelligence sharing, and de Havilland had refined it into the H-1B Goblin engine, producing 2,460 pounds of thrust. Johnson's team built the airframe around it in 3 shifts, 24 hours a day, 7 days a week. They machined parts in the morning, assembled them in the afternoon, and tested systems at night. When rivets didn't arrive on schedule, Johnson sent engineers to hardware stores across Los Angeles County. When aluminum sheets came in wrong specifications, they cut and reformed them on site. The XP-80 first flew on January 8, 1944, from Muroc Army Airfield in the Mojave Desert. Test pilot Milo Burcham took it to 20,000 feet and hit 502 miles per hour, faster than any American fighter then operational. The jet age had arrived in the United States, and Johnson had compressed years of development into 20 weeks. The Army ordered 5,000 P-80s before the prototype finished flight testing. Most arrived too late for World War II. But Johnson had proven something more valuable than a single aircraft design. He'd proven that revolutionary technology didn't require massive organizations. It required the right people, minimal interference, and absolute focus. The Skunk Works model, small teams operating with unusual autonomy, became Johnson's template. Over the next 4 decades, he'd use it to build the U-2 spy plane, the F-104 Starfighter, and eventually the SR-71 Blackbird. But in 1943, standing in that circus tent, with the smell of melting plastic burning his nostrils, Johnson was still learning the fundamental lesson. Speed comes from trust, and innovation dies in committees. Francis Gary Powers sat in the cockpit of his U-2 spy plane at 7,500 feet over Sverdlovsk, Russia, when the first SA-2 surface-to-air missile detonated close enough to rip his aircraft apart. The date was May 1, 1960, a Sunday morning that ended 15 years of American high-altitude invincibility. Powers ejected, parachuted into Soviet custody, and triggered an international crisis that reached President Eisenhower's desk within hours. The U-2 program, Kelly Johnson's greatest achievement to that point, had just proven fatally vulnerable. Johnson had designed the U-2 in 1955 specifically to fly above Soviet missiles and interceptors. The CIA wanted reconnaissance photographs of Russian military installations, and Johnson promised them an aircraft that could cruise at 70,000 feet. higher than any Soviet weapon could reach. He'd been right for 5 years. U-2 pilots had flown dozens of missions over Russia, photographing airfields, missile sites, and nuclear facilities with cameras capable of reading license plates from 13 miles up. The Soviets tracked them on radar, scrambled interceptors that couldn't climb high enough, and fired missiles that couldn't reach the altitude. Until Sverdlovsk. The SA-2 guideline missile that killed Power's U-2 represented a technological leap Johnson hadn't anticipated. Soviet engineers had developed a 2-stage rocket with enough thrust to reach 80,000 feet and a proximity fuse sensitive enough to detonate near a target without direct impact. The missile climbed to Power's altitude, exploded 70 feet behind his aircraft, and sent shrapnel through the U-2's fragile airframe. Power survived. The doctrine of high-altitude sanctuary did not. Eisenhower convened emergency meetings at the White House. The U-2 shootdown had exposed American reconnaissance operations publicly, embarrassed the administration before a planned summit with Soviet Premier Nikita Khrushchev, and, most critically, revealed that America's primary intelligence-gathering platform was now obsolete. The president's directive to the CIA was unambiguous. Develop an aircraft the Soviets cannot shoot down. Not today, not 5 years from now, not ever. The Pentagon and CIA began studying options immediately. Some analysts proposed flying even higher, pushing to 100,000 feet, where thinner air made missile interception theoretically impossible. Others suggested flying lower and faster, using speed to outrun missiles rather than altitude to avoid them. Johnson, brought into early discussions, understood that altitude alone had failed. The Soviets would continue improving their missiles, and any altitude ceiling would eventually become obsolete. Speed offered a different equation. A missile launched at an aircraft moving Mach 3 would have to predict where that aircraft would be in the time it took the missile to climb, accelerate, and reach intercept altitude. The geometry favored the aircraft, not the missile. But Mach 3 was theoretical territory in 1960. The fastest operational aircraft in American service, the F-104 Starfighter, another Johnson design, barely exceeded Mach 2 in level flight. Reaching Mach 3 and sustaining it for thousands of miles required solving problems in aerodynamics, propulsion, materials, and thermal management that had never been addressed simultaneously. Johnson's preliminary calculations suggested skin temperatures around 600 degrees Fahrenheit at Mach 3, hot enough to weaken aluminum structures and boil conventional aviation fuel. The CIA gave Johnson a contract in late 1959, 7 months before Powers went down. The shootdown transformed that contract from experimental research into national priority. America needed an untouchable reconnaissance aircraft, and Johnson had 18 months to design one. He called the project Archangel. The designation was A-12. The Blackbird was beginning. Johnson's engineers discovered the titanium problem 3 months into the A-12 design when test samples started cracking in the Skunk Works metallurgy lab. They'd ordered the purest titanium available, supposedly aerospace grade from American suppliers, and subjected small sections to the thermal cycles expected at Mach 3. The metal fractured along grain boundaries, developed surface cracks, and showed brittleness that made it useless for airframe construction. Johnson initially suspected contamination during testing. The truth was worse. Titanium in its raw form is remarkably strong and lightweight, with a strength-to-weight ratio superior to aluminum and the ability to maintain structural integrity at temperatures exceeding 600 degrees Fahrenheit. But titanium is also chemically reactive during processing. Exposure to chlorine, even in trace amounts, creates titanium tetrachloride, a compound that embrittles the metal and destroys its mechanical properties. The Burbank municipal water supply Johnson's team discovered contained chlorine added for purification. Every time they washed titanium parts before welding or forming, they were poisoning the metal. The solution required installing distilled water systems throughout the Skunk Works facility. But the chlorine problem revealed a larger issue. American titanium production was primitive in 1959. The United States had minimal industrial capacity for processing titanium ore into high-quality aerospace alloys. Most domestic titanium went to experimental programs in small quantities, and suppliers couldn't guarantee consistent purity. Johnson needed millions of pounds of titanium for the A-12 airframe. 93% of the aircraft's structure would be titanium, and American sources couldn't provide it. The CIA quietly arranged purchases through shell corporations operating in third countries. The world's largest titanium supplier turned out to be the Soviet Union, which had developed extensive processing facilities to support its own aerospace programs. Johnson's team was building an aircraft designed to spy on Russia using titanium secretly purchased from Russian mines and refineries. The irony wasn't lost on anyone at Skunk Works, but pragmatism overrode politics. If Soviet titanium was the purest available, they'd use Soviet titanium. Even with quality material secured, working with titanium demanded entirely new manufacturing processes. Conventional cutting tools wore out in minutes against titanium's hardness. Drill bits designed for aluminum shattered. Welding titanium required inert gas environments to prevent oxidation. Any oxygen exposure during welding created brittle, porous joints. Johnson's machinists had to learn titanium's quirks through expensive trial and error. Early test panels cost $50,000 each and frequently ended up scrapped. Cadmium-plated tools, standard in aerospace manufacturing, caused unexpected galvanic corrosion when they contacted titanium. Johnson banned cadmium entirely from the Skunk Works facility. Summer heat created additional problems. Titanium parts, machined in temperatures above 70 degrees Fahrenheit, showed dimensional changes as they cooled, throwing off tolerances. The shop floor required climate control year-round. Even marking titanium panels with standard ink pens caused corrosion. Engineers had to use special marking compounds. The costs multiplied beyond original estimates. Each A-12 consumed 85,000 pounds of titanium, machined down from 165,000 pounds of raw stock. Nearly half the material ended up as shavings on the shop floor. Special tooling, climate-controlled facilities, and the learning curve for titanium fabrication pushed the A-12 program budget past $30 million per aircraft. But Johnson had no alternatives. Aluminum melted at Mach 3 temperatures. Steel was too heavy. Titanium, despite its difficulties, remained the only material that could survive sustained flight at triple sonic speeds. So Johnson's team kept drilling, welding, and cursing the most difficult metal they'd ever encountered. The Blackbird would be built from Russian titanium, or it wouldn't be built at all. Johnson's thermodynamics team calculated that the A-12's leading edges would reach 1,050 degrees Fahrenheit at Mach 3.2, but the real problem sat 6 feet behind the nose. Air friction at triple sonic speeds would heat the aircraft's titanium skin to sustained temperatures between 400 and 600 degrees Fahrenheit across most of the fuselage, with localized hotspots near the engines exceeding 900 degrees. The aircraft would grow 11 inches longer in flight as the titanium expanded. Fuel tanks would stretch. Panels would warp. Every system designed in the cool precision of the Skunk Works engineering offices would face a thermal environment equivalent to a commercial oven set to broil. Conventional aviation fuel presented the first crisis. JP-4, standard in Air Force jets, has a flash point of 110 degrees Fahrenheit, the temperature at which fuel vapors ignite. With skin temperatures routinely exceeding 400 degrees, JP-4 would boil in the tanks and detonate from heat transfer through the tank walls. Johnson needed fuel that remained stable above 600 degrees. Shell Oil developed JP-7 specifically for the A-12 program, a specialized kerosene blend with a flash point of 140 degrees Fahrenheit and thermal stability to 450 degrees. JP-7 was so stable it wouldn't ignite from a lit match. Test pilots demonstrated this party trick repeatedly. The trade-off was that JP-7 required chemical igniters to start the engines, adding complexity to every startup sequence. But even JP-7 needed cooling. Johnson's solution turned the fuel into a heat sink. JP-7 would flow through channels in the aircraft's skin before reaching the engines, absorbing thermal energy from the hot titanium and carrying it away. The fuel entered the system at ambient temperature, circulated through cooling passages around the engines and leading edges, and arrived at the engine inlets preheated to 300 degrees Fahrenheit, hot enough to improve combustion efficiency. The system worked thermodynamically, but it required fuel to start flowing before the engines generated enough heat to need cooling, creating a chicken and egg problem during ground operations. Hydraulic fluid posed similar challenges. Standard hydraulic systems used petroleum-based fluids that degraded rapidly above 200 degrees Fahrenheit. Johnson's team developed a synthetic fluid based on methyl silicone that maintained viscosity and lubrication properties to 600 degrees. The fluid cost $400 per gallon compared to $3 for conventional hydraulic fluid, but it was the only option. Every hydraulic line, actuator, and pump in the A-12 had to be redesigned around the new fluid's different viscosity and thermal expansion characteristics. Rubber seals and gaskets simply ceased to exist as options. Natural and synthetic rubbers decompose at temperatures below 400 degrees Fahrenheit. Johnson's engineers specified Viton fluoroelastomer seals throughout the aircraft, a material developed by DuPont that maintained flexibility and sealing properties to 500 degrees. But Viton seals leaked when cold. A-12 aircraft sitting on the runway would drip JP-7 from tank seams, hydraulic fluid from actuator shafts, and lubricants from bearing assemblies. Ground crews learned to position drip pans under parked Blackbirds as standard procedure. The leaks stopped once the aircraft reached operating temperature, and thermal expansion sealed the gaps. But every A-12 left a small petroleum puddle wherever it parked. Electrical systems required similar adaptations. Standard wire insulation melted at 300 degrees. Johnson specified Teflon-insulated wiring throughout the aircraft, accepting the added cost and reduced flexibility. Cockpit instruments faced glass covers that could withstand sustained heat without warping. Even the pilot's canopy required special treatment. Standard acrylic canopies would soften and distort at Mach 3 temperatures. Johnson used quartz composite panels with multiple layers and air gaps for thermal insulation. The heat problem touched every system, every component, every design decision. The air-breathing jet engine stops functioning above Mach 2.5 unless you solve a problem that seems physically impossible. You have to slow supersonic air to subsonic speeds before it reaches the engine compressor, and you have to do it without killing your forward momentum. Johnson's team faced this challenge knowing that the J-58 turbojet engines Pratt & Whitney was developing could only ingest air moving slower than 500 miles per hour. At Mach 3.2, the A-12 would be flying at 2,200 miles per hour. The inlet had to decelerate that air by 1,200 miles per hour across a distance of roughly 12 feet. The solution was a movable spike, a conical centerpiece that projected forward from each engine nacelle and could slide hydraulically in and out during flight. At subsonic speeds, the spike retracted fully, allowing maximum airflow into the engine. As the aircraft accelerated toward Mach 1, the spike extended forward, creating a shockwave pattern that began compressing and slowing the incoming air. By Mach 3, the spike extended 26 inches forward, generating a series of oblique shockwaves that acted like invisible speed bumps in the airstream. Johnson's aerodynamicist, Ben Rich, calculated the shockwave geometry obsessively. The spike had to position itself precisely to create multiple compression waves that intersected at specific points in the inlet duct. Too far forward and the shockwaves would create turbulence that starved the engine. Too far back and supersonic air would reach the compressor blades, creating shockwaves inside the engine that would destroy it in seconds. The tolerance was measured in fractions of an inch at speeds where the aircraft covered 3 football fields per second. The inlet system did more than slow the air. It had to compress it. At Mach 3.2, ram compression from the inlet geometry provided 90% of the total engine thrust. The turbojet engine itself became almost secondary. The J58 compressor added minimal compression compared to what the inlet achieved through pure aerodynamic shaping. Johnson had essentially invented a ramjet wrapped around a turbojet, using the turbojet primarily to get the aircraft up to ramjet speeds. Bypass tubes added another layer of complexity. At high Mach numbers, the inlet captured more air than the engine could consume. Excess air had to go somewhere, or it would back up and choke the inlet. Johnson added 6 bypass tubes around each engine that could vent excess air overboard, bleeding it around the engine and ejecting it through the aft section to generate additional thrust. The bypass system was continuously variable, opening and closing automatically based on inlet pressure readings to maintain optimal airflow. The entire inlet control system operated automatically through an analog computer that monitored 50 different parameters, hundreds of times per second. Inlet pressure, spike position, bypass door angles, engine RPM, altitude, and Mach number all fed into calculations that adjusted spike position in real time. Pilots could override the system manually, but doing so was dangerous. Mismanaging the inlet at Mach 3 could cause an unstart, where the shockwave pattern collapsed and supersonic air suddenly slammed into the compressor. Unstarts created instantaneous loss of thrust on one engine, violent yaw, and side loads exceeding 6 times the force of gravity. Test pilots described unstarts as getting hit by a telephone pole at highway speeds. Johnson tested inlet configurations for 2 years before finalizing the design. Wind tunnel models at NASA's Ames Research Center validated the shockwave patterns. Ground tests at Pratt & Whitney confirmed the J58 could survive the thermal environment. But the real test would come at Mach 3 and 80,000 feet, where theory met titanium and physics stopped being forgiving. Johnson knew the inlet was the most sophisticated air-breathing propulsion system ever designed. He also knew it had to work perfectly on the first flight, or the test pilot wouldn't come home. Lou Schoch pushed the A-12's throttles forward on April 26, 1962, at Groom Lake, Nevada, a dry lake bed the CIA called Area 51 for security reasons that had nothing to do with aliens and everything to do with keeping Kelly Johnson's latest creation invisible to Soviet satellites. The aircraft was officially designated Article 121, the first A-12 prototype capable of powered flight. Schoch had specific instructions from Johnson. Take it to 400 miles per hour, lift off, climb to 30,000 feet, make 1 circuit of the lake bed, and bring it home. No supersonic runs, no pushing limits. This was a shakedown flight to verify that the thing could actually fly. Schoch reached rotation speed and pulled back on the stick. The A-12 lifted cleanly, gear retracted, and everything felt normal for exactly 90 seconds. Then the master caution light illuminated. Hydraulic pressure in the primary system was dropping. Schoch watched the gauge needle fall from 3,000 psi toward 0 while running through emergency checklists in his head. The A-12 had dual hydraulic systems for redundancy. Lose one, and you still had flight controls. But the backup system gauge was also dropping. Total hydraulic failure at 400 miles per hour with the most expensive aircraft in America underneath him. Schoch's training was test pilot pragmatic. Assess the situation, identify options, execute the best one available. Option 1 was ejection. The A-12 carried a rocket-boosted ejection seat rated to 80,000 feet and Mach 3. Schoch rejected that immediately. Ejection would destroy the only A-12 prototype capable of flight and set the program back 18 months. Option 2 was attempting a dead stick landing with no hydraulics, which meant no flight controls, no landing gear extension, and no brakes. That option would also destroy the aircraft and had reasonable odds of killing him. Option 3 required assumptions. If the hydraulic lines were leaking, but not completely empty, residual pressure might give him partial control authority, enough to maneuver but not enough for normal landing procedures. Schalk tested the flight controls gently. The stick felt mushy, but responsive. He had maybe 20% normal control effectiveness. The gear indicator showed gear down and locked, which meant the gear had gravity dropped when hydraulic pressure failed. A backup feature Johnson's designers had included precisely for this scenario. Schalk aligned himself with the lakebed runway, a 13,000-foot strip of packed dirt marked with orange cones. Without hydraulic pressure, he had no brakes and minimal nose-wheel steering. The landing would be entirely momentum-based. Touch down, hold the nose up with what little elevator authority remained, let the drag slow him, and hope 13,000 feet was enough. He came in flat, airspeed higher than normal, because he couldn't risk dropping too slow and losing what little control he had. The main gear contacted at 210 miles per hour. Schalk held the nose up as long as aerodynamic forces allowed, then let it settle onto the nose wheel. The A-12 rolled straight down the centerline for 8,000 feet before wind resistance and friction brought it to a stop. Schalk shut down the engines, popped the canopy, and waited for the chase vehicles racing across the lakebed. He was 52 years old, had been flying experimental aircraft for Lockheed since 1954, and had just saved Kelly Johnson's program from catastrophic failure. Post-flight inspection revealed a hydraulic line rupture caused by vibration fatigue, a failure mode the ground test program hadn't replicated. Johnson's team redesigned the hydraulic routing with additional dampening and reinforcement. Schalk flew Article 121 again 3 weeks later. This time, everything worked. The A-12 went supersonic on its 9th flight in May 1962 and reached Mach 2 before summer ended. Johnson had his proof of concept. Now he had to make it operational. The SR-71 Blackbird first crossed into North Vietnamese airspace on March 21, 1968, cruising at 80,000 feet and Mach 3.1 over Hanoi. Surface-to-air missile sites tracked the aircraft on radar, computed firing solutions, and launched SA-2 missiles that climbed desperately toward the target. The missiles ran out of energy at 65,000 feet, 15,000 feet below the Blackbird's flight path. North Vietnamese missile operators watched their most advanced weapons fall uselessly back to Earth, while the American reconnaissance aircraft photographed targets with impunity. They would fire at SR-71s 799 more times over the next 4 years. They never came close to hitting one. The Strategic Air Command deployed SR-71s to Kadena Air Base in Okinawa specifically for missions over Southeast Asia, North Korea, and China. Each mission required 6 hours of pre-flight preparation, including filling the fuel tanks with JP-7, preheating the engines, and aligning the inertial navigation system, technology so precise it could guide the aircraft across 3,000 miles with position accuracy within 100 feet. Pilots wore full-pressure suits identical to those worn by Gemini astronauts because cabin decompression at 80,000 feet meant instant death. The North Vietnamese fired roughly 800 surface-to-air missiles at SR-71s between 1968 and 1972, with 0 successful intercepts. Soviet-made SA-2 missiles had maximum altitude ceilings around 70,000 feet under optimal conditions. The Blackbird cruised 10 to 15,000 feet higher while moving faster than any missile could track. Missile guidance systems of the 1960s calculated intercept trajectories based on target speed and heading. Against an aircraft moving Mach 3, those calculations required predicting where the target would be in the 30 to 40 seconds it took a missile to climb from ground level to intercept altitude. At 2,200 miles per hour, the Blackbird covered 12 miles in those 40 seconds, faster than missile guidance computers could compensate. North Vietnamese operators tried salvos, launching 4 to 6 missiles simultaneously to saturate the intercept zone. The geometry still favored the Blackbird. Each missile had a lethal radius of roughly 200 feet. 6 missiles created a kill zone 1,200 feet across. The Blackbird, moving at 2,200 miles per hour, covered that distance in half a second, requiring impossible precision in timing and trajectory calculation. Even if operators fired missiles early to lead the target, the Blackbird's speed meant it would be miles past the predicted intercept point before missiles arrived. Soviet MiG-25 interceptors represented a more serious threat. The MiG-25 was designed specifically to intercept high-altitude bombers and could reach 80,000 feet in a zoom climb. Though it couldn't sustain that altitude, Soviet pilots attempted intercepts over North Vietnam on several occasions, climbing to maximum altitude and firing air-to-air missiles at detected radar targets. None succeeded. The MiG-25's radar couldn't maintain lock on the Blackbird's small radar cross-section, and even when pilots got close enough to fire, their missiles lacked the speed to catch an aircraft already moving Mach 3. One SR-71 pilot over North Vietnam reported having 12 missiles fired at his aircraft during a single mission. He watched the contrails climb toward him, fall away short of his altitude, and tumble back toward the jungle below. The Blackbird's defensive system consisted entirely of speed and altitude. No countermeasures, no defensive weapons, no evasive maneuvers required. Kelly Johnson had designed an aircraft that made traditional air defense irrelevant through physics rather than stealth. After 4 years and 800 missile launches, North Vietnamese operators stopped trying. The Blackbird had proven itself untouchable, not through luck or pilot skill, but through engineering that exceeded every weapon designed to destroy it. The SR-71 crossed into Swedish airspace on June 29, 1987, at 73,000 feet on a reconnaissance mission photographing Soviet naval installations around the Baltic Sea. Swedish radar operators detected the incursion immediately and notified Soviet Air Defense Command at Kaliningrad. 6 MiG-25 interceptors scrambled from bases in Estonia and Latvia within 4 minutes. The Cold War's most sophisticated game of cat and mouse was beginning, and the cat had no chance of catching anything. Soviet pilots pushed their MiG-25s into maximum performance climbs, afterburners lit, climbing at 40,000 feet per minute toward the American intruder. The MiG-25 Foxbat was specifically designed to intercept high-altitude bombers and reconnaissance aircraft. It could reach 80,000 feet in a zoom climb and carried R-40 air-to-air missiles with a maximum range of 35 miles. Soviet doctrine called for multiple interceptors approaching from different vectors to bracket the target and force it into a kill zone where at least one aircraft would achieve missile lock. The SR-71 pilot monitored his defensive systems officer's radar warning receiver, which displayed the MiG positions as they climbed toward intercept geometry. Standard Blackbird procedure for interceptor threats was simple: accelerate. The pilot pushed the throttles to maximum continuous power, watched the Mach meter climb past 3.0, and continued his planned reconnaissance route. The MiGs reached 75,000 feet, 8,000 feet below the Blackbird, and fired missiles at maximum range, hoping for a lucky hit. The R-40 missiles climbed toward the target, but couldn't maintain enough energy at that altitude to close the distance against an aircraft moving 2,200 miles per hour. The geometry was brutal for the Soviet pilots. Their aircraft were already at maximum sustainable altitude, engines starving for oxygen in the thin air, and the target was still above them, moving 3 times faster than they were. The MiG-25's maximum speed at altitude was Mach 2.83, impressive by any standard, except when chasing something capable of Mach 3.2. The Blackbird pulled away from the interceptors at roughly 400 miles per hour, opening the distance faster than the MiGs could close it, even with afterburners consuming fuel at catastrophic rates. Soviet pilots had roughly 10 minutes of fuel remaining at full afterburner before they'd have to break off and return to base. The SR-71 carried 80,000 pounds of JP-7, giving it a mission endurance exceeding 3 hours at cruise speed. The interceptors were sprinting while the Blackbird was jogging. After 8 minutes of futile pursuit, the lead MiG pilot acknowledged reality and called bingo fuel, the point where remaining fuel was only sufficient to reach the nearest airfield. All 6 MiGs broke pursuit simultaneously and descended toward their bases. The SR-71 continued its reconnaissance run uninterrupted. The mission collected photographs of Soviet submarine facilities at Baltijsk, naval shipyards at Kaliningrad, and radar installations along the Estonian coast. The Blackbird's cameras operated at 80,000 feet, with resolution sufficient to identify individual vehicles and read hull numbers on ships. Swedish and Soviet officials both filed diplomatic protests with the United States about the airspace violation. The U.S. State Department offered neither confirmation nor denial, standard procedure for SR-71 missions. The aircraft landed at RAF Mildenhall in England 4 hours after takeoff, having covered 3,200 miles, including the Baltic reconnaissance run and the return flight. Soviet Air Defense Command analyzed the intercept attempt and concluded what they'd known since the Blackbird entered service. They had no effective counter to an aircraft that flew higher and faster than anything in their inventory. The MiG-25 remained their best interceptor, and it had just demonstrated complete inability to threaten the SR-71. Kelly Johnson's design had achieved absolute air superiority through speed alone. No stealth technology, no electronic countermeasures, just physics that made interception impossible. The SR-71 made its final operational flight on March 6, 1990, landing at Palmdale, California, after a coast-to-coast speed run that took exactly 1 hour, 7 minutes, and 54 seconds from Los Angeles to Washington, D.C., an average speed of 2,924 miles per hour. Air Force officials parked the Blackbird fleet, citing operational costs and the arrival of satellite reconnaissance that could photograph targets without violating airspace. But the real reason sat in Kelly Johnson's original design specifications. Nobody had built anything faster in the 3 decades since the first A-12 prototype flew. Johnson retired from Lockheed in 1975 at age 65, having spent 44 years at the company and 32 years running Skunk Works. His legacy included 40 aircraft designs, but the SR-71 remained his masterpiece, the physical embodiment of how far engineering could push against physics when freed from bureaucratic constraint. The aircraft held 85 world records for speed and altitude, most of which still stand. The absolute speed record of 2,193 miles per hour, set by SR-71 pilot Eldon Joers in 1976, has never been exceeded by any air-breathing aircraft. Modern military aviation moved toward stealth after the Blackbird's retirement. The F-117 Nighthawk and B-2 Spirit bomber used radar-absorbent materials and geometric shaping to become invisible rather than untouchable. Engineers chose radar cross-section reduction over raw speed, betting that invisibility provided better survivability than Mach 3 performance. The bet proved correct for specific mission profiles, but stealth came with compromises: limited weapons payload, subsonic cruise speeds, vulnerability to low-frequency radar systems. Johnson's approach had been the opposite: be completely visible and move too fast for anyone to do anything about it. The SR-71's operational costs were legitimately extraordinary: $85,000 per flight hour, including fuel, maintenance, and support equipment. Each aircraft required specialized facilities, trained ground crews, and JP-7 fuel that cost 10 times more than standard jet fuel. But those costs reflected the price of sustained Mach 3 flight, not inefficient design. Johnson had built the only aircraft in history that could cruise at triple-sonic speeds for hours at a time. The engineering required to survive those conditions, titanium construction, inlet controls, thermal management systems, had no cheaper alternatives. Kelly Johnson died on December 21, 1990, 9 months after the last Blackbird landed. He was 80 years old and had lived to see every major American military aircraft of the jet age, many of which he had personally designed. The SR-71 flew for 34 years across multiple wars and crises without losing a single aircraft to enemy action. Missiles failed to reach it. Interceptors couldn't catch it. The aircraft's perfect operational record stood as testament to engineering that exceeded every threat by comfortable margins, rather than minimal ones. NASA briefly operated two SR-71s for high-speed research after Air Force retirement, flying them until 1999 for experiments in supersonic aerodynamics and propulsion. Those final flights demonstrated that Johnson's 50-year-old design still outperformed modern alternatives in raw speed capability. Several proposals emerged to develop an SR-71 replacement: Aurora, SR-72, various hypersonic concepts, but none progressed beyond preliminary studies. The engineering challenges Johnson solved in 1960 remain difficult in 2025, and the operational requirements for a Mach 3 reconnaissance aircraft remain questionable when satellites and stealth platforms provide alternatives. The Blackbird sits in museums now across America, titanium skin still bearing the thermal stress patterns from Mach 3 flight. Visitors walk around the aircraft and struggle to believe something designed before computers, before finite element analysis, before computer-aided design software, could fly 3 times the speed of sound at altitudes where the sky turns black. Kelly Johnson proved what human engineering could achieve when brilliant people were trusted to solve impossible problems. The SR-71 remains his answer, written in titanium and still unmatched